Hello, welcome back to part 2, and we're going to continue our discussion today on the antiderivative. And another way we can talk about derivatives is using something that we call a differential equation. Very simply, a differential equation is any equation that contains a derivative. And we have a couple of examples down here. Here we have dy dx is equal to 3x squared plus 4x. And we have f prime of x, which is sine of x minus 4. And if you notice, we're using that Newtonian notation, and we're also using that Leibniz notation. These are both called differential equations because they are derivatives. Today, what we want to start talking about is how can we solve a differential equation. To do this, we have to undo the derivative itself. And it is quite simple to do. So let's look at our first example. We want to solve the following differentials. Now notice they're telling us the derivative of our function is 3x squared. What we want to do to solve this, we want to know what function has the derivative 3x squared. And this we can easily do in terms of product rule. We know to take the derivative, we drop the power, made it 3, and we subtract 1. Well, if my subtraction 1 gave me 2, it tells me that the original function had to be x cubed. Well, that's one option. Another option we could have x cubed plus 10. If I were to take the derivative of x cubed and x cubed plus 10, would we not get 3x squared in both cases? And the answer, of course, is yes. We can even be more fancy if we like. We can even say, oh, look, let this be x cubed plus pi. Same thing. 10 and pi, they're both constants. When we took the derivative, they became 0. So even though I have 3 different functions, they all have the exact same derivative. So we should notice the constant can be anything. And that is because the derivative of any constant is just 0. So when we undo that derivative, we could wind up with anything as a constant. So to help us write these, we have what's called a general solution. So our general solution, we would say this. The original function, remember my derivative is f prime, so my original function would be f of x equals x cubed plus, now I need to write something that can identify this as just a general constant. So what we use is C1. Now the subscript right here, we're going to talk a lot about this over the next few days. I know a lot of scientists, they do prefer the C1s. In some books, you'll just see a C, and that's okay. But I myself, I like the C1 right there. We'll see why we do that as we go further and further into these units. And this is what we call the general solution, or this is what we call the antiderivative of the derivative f prime of x. It is called an antiderivative because we did the exact opposite of the derivative itself. Given the derivative, we undid the derivative by finding the original function. So what this does is this finds what the original function was. So if we think about it like this way, if I'm given velocity, this is kind of giving us our position curve. And that's what this says down here. The general solution of f of x is what we call the antiderivative of f of x. And this is very helpful if we think of the function and the derivative as inverse operations. In other words, they undo each other. They cancel each other out, like we saw in the example in the previous video, where we can add, what's the inverse of addition? Subtraction. They cancel each other out. A few quick definitions, and then we'll go into some examples here today. One, the plus C1 is what we call the constant of integration. The solution to the general antiderivative is what we call an indefinite integral. You might recall in a previous video we talked about the definite integral and how it finds area. And you might remember that a definite integral, which we'll talk about later on, has bounds on it. We call it indefinite because we really don't know what this C is. Indefinite means I don't know exactly. I can't know the actual answer because I don't know what C is. In a couple of days, we'll talk about how we can actually solve it, though. The indefinite integral is what we call not unique, as that plus C could be anything. So we're going to talk a lot about uniqueness. And we saw that up here. If we notice, this x cubed, we got x cubed plus 10, x cubed plus 3. All of these have the same derivative, but they're not unique because unique means there can only be one exact answer. And that's what it means to be unique. So since this C could be anything, that constant of integration could be anything, we say that the indefinite integral is what we call not unique. The symbol, which we saw when we talked about the definite integral, in the definite integral we said that this is, and it means to add an infinite sum, is something we call an integrand. Not an integral, called an integrand. Sorry about that. That's called a misspelling. It's called an integrand, and it means that we're going to add up an infinite sum. And we're going to get to those later on. Last unit we talked about Riemann sums and how we could approximate the actual area by using rectangles and trapezoids. Later on, we're going to use this symbol right here and what we're talking about today to get the actual area. This is also what we call the symbol for the antiderivative. So it's like an operation where if you see this symbol, this of course means to add. You see this symbol, of course it means to multiply. Well, to a mathematician, this symbol means to find the antiderivative. It's just a symbol for us telling us what to do. We saw this, again, symbol when we learned about area under a curve. So let's talk about the difference between what we call a definite integral and an indefinite integral. A definite integral, what we talked about last time, this has a starting and an ending limit or bound. So that was this a to b f of x dx. And we said that this finds area last unit. An indefinite integral has no bounds or limit. This is just what we call the antiderivative. There is a relationship to them. The antiderivative, if we know the bounds, we can find the actual area under a curve. And we're going to talk about that in a few days there. But I know what you guys want to get to right now. You want to get to a wonderful example here. So, some quick rules. Well, the antiderivative of 0. Well, we're saying that the derivative of something is 0. Well, what's the only way? Well, if I have a constant, if y is 5, I know the derivative is 0. So the antiderivative of 0 is just some random constant. Just plus is just C1. It's just some random constant. If I have k, well, k is just a number. And when we talk about the power rule, we'll see what this is. This is just going to become kx. This is like saying if I have y is equal to 5x. Well, I know the derivative is just some constant. So, and I just need to put the x there. So we go plus c1. And if I have a constant times something, this just says I can factor out that constant. We saw this last unit when we were talking about looking at areas and Riemann sums. Here, same rule as last time. Last unit, we can split an antiderivative, go plus or minus g of x dx. Just be careful. It's kind of like we're going to distribute the integral, and we're going to distribute that dx to both of them. And this is what we're getting to. The power rule is for power functions. So what this is saying is if I have a derivative, and it's x to the n, a function x to the n, I know to get the derivative, my rule says to drop that power, and we subtract 1. Well, to do the antiderivative, we are going to do the inverse of this. So our rule is the exact opposite. Instead of subtracting 1, we are going to add 1 to the power. And instead of multiplying by n, we're going to divide by this n plus 1, our new power. So we get x to the n plus 1 over n plus 1, and then you get your constant. So you're going to add, divide, and add your c right there. And there's our rule for the power rule. So let's look at an example, and then we'll go on to the next video, okay? So really simple. So if we have our antiderivative of 3x squared, what we want to find is the original function here. So to get the original function, what our rule says to do, remember, we want to use what's called the antiderivative here. So my rule says to add 1 to the power. So I'm going to get this 3x. That becomes 3x cubed, and then I'm going to divide by that new power. 2 plus 1 is 3, so I divide by 3. And don't forget to add the plus c. You need this, because if this is my derivative here, it had a constant, it just became 0. We don't know what the constant is, we just put that plus c. So our final answer is just going to be x cubed plus c1. And there is our antiderivative. All right, go to the next video and we'll take a look at a bunch more examples. I will see you then.